Okay, so next speaker is Professor Youngjun Kim from University of Toronto, and he's going to talk about the structure and magnetic anisotropy of alpha-Rucl3 chloride.
Thank you. Thanks for the introduction, and then I'd like to thank the organizers for inviting me to this very interesting workshop. I'm learning a lot, and so I'm happy to share some of my research results in recent years, which may not be necessarily or sort of kind of directly fit into the condensed matter solitons, but it's very nice actually talk following Dr. Huang's very nice introduction about the Kitaev model, and a very interesting model, and then perhaps we'll see actually how realistic that realization might be, because I'll be actually talking about the interlayer couplings. Also, I'm an experimentalist, as you can sort of see from my title, so I won't be answering any questions about the topological defects. All right, so okay, oh yeah, so before starting this, we're going to so I'm going to acknowledge this work that has been going on for a while. Actually, it's been almost like 10 years since we started working on this material, alpha-ruthenium chloride, and then this all sort of come from contributions from a lot of collaborators, and also the generations of PhD and postdoc in our group. So so kind of trying to single out Subin Kim, who's the graduate student who's just finishing up his work, and then most of the work that I'm going to tell you today is his actually his PhD thesis, and we have tremendously benefited from the discussions in the resident theorists at the University of Toronto, Professor Youngjun Kim and Professor Hae-young Hee and their students, as well as a collaboration with the Louis Talifier group at Sherbrooke, and also we have done a lot of work at the synchrotrons and neutron facilities all over the world, as shown here. So yeah, so this is the outline, and that's how it looks like. So I'm going to give a very brief introduction, because we heard actually a sort of very detailed introduction about Kitaev quantum spin liquid. So what I'm going to focus on is actually kind of translating this amazing properties of Kitaev quantum spin liquid into real materials, and sort of I talk about the mechanism and also the material, and focus on the two aspects of this alpha-ruthenium chloride, which is a crystal structure and magnetic structure. And you might wonder, I mean, isn't this actually sort of kind of day one thing that you all understand going into this kind of research? And it turns out that this is actually a very long and interesting history, because we don't actually have a clear, or until now, in my opinion, understanding of crystal structure and magnetic structure. So that's actually what I'm going to sort of get into today. So right, so we heard about herber-smithite, and we heard about alpha-ruthenium chloride. So actually, I'll just skip this right away. And then we heard about many of these things about the Heisenberg model on Kagome lattices describing herber-smithite, and then Kitaev's honeycomb model is describing alpha-ruthenium chloride. What I just want to point out here is that sort of a situation is somewhat different, because here there's a sort of a general agreement that this is a model that describes herber-smithite, and then there is a little bit more theoretical sort of nuanced discussions about the quantum spin liquid of this model. However, in the Kitaev's honeycomb model and alpha-ruthenium chloride, the situation is reversed, because everybody agrees and understands what kind of quantum spin liquid this model realizes. But the question actually is alpha-ruthenium chloride a good realization of Kitaev quantum honeycomb model? And that is actually sort of still the question that we are trying to answer in many of our studies. Okay, so I can skip this. So we heard a lot about this, how to solve this using Majorana fermions, and then there is interesting aspects of Kitaev model, because you can actually realize anyons, and especially non-abelian anyons that is used for topological quantum computing. And basically that's what every funding proposal we write is basically we are studying this, because it might be leading to topological quantum computing. Okay, so real talk, I'm going to start with this one. So So it probably many of you are familiar with this work. So initially, when the Kitaev model was written, it is an exact solvable model, and it is actually exactly solved model. That's actually there's a difference between solvable and solved, right? So it was solved in the first paper written by Kitaev, and so, but it was actually somewhat far-reaching. I mean, so kind of when people think about this, how can you actually realize that kind of a bond-dependent ion interaction in honeycomb lattice? And so this kind of solution was provided by this idea by Jacqueline and Kalulin. And if we actually basically realize start with something like a very strong spin orbit coupled material like iridates or other sort of a very heavy element, transition metal elements. And if we have to start with 5D electrons and you sort of turn on the crystal field levels and spin orbit coupling and so on, and if you do all this kind of chemical massaging, then you end up with the ground state of J effective equal half state, or sometimes called Kramer's doublet state. So this is effective spin half system that will be responsible for Kitaev's model. And the important thing there is that it actually has orbital and spin degrees of freedom mixed in. So why is it important? Because orbital means that there's a spatial aspect, unlike just the spin degrees of freedom. And because of that aspect, you can basically encode this spatial and the bond dependent into this model. So the solution or the prescription is, if you take this kind of octahedral and then connect them using so-called edge sharing geometry, then you can realize so-called bond-dependent interactions. And by putting together these things into a honeycomb lattice, so this kind of edge sharing interaction, edge sharing octahedra can be sort of put together very naturally in this way. So in this way, and then form something like this. This was actually first realized in iridates, but iridates are not so kind of experimentalist friendly because of its sort of difficulty of doing neutron scaring. So that's basically where we sort of came up with sort of using a ruthenium chloride, which is actually neutron friendly material, and then has exactly the type of crystal structure that it is prescribed by Jacqueline-Kalulin mechanism. And since then, I think a lot of work has been done on this material, and none other than this one that became really important. And this remarkable study is published in 2018 by Yuji Matsuda group here. So we heard a little bit about this work from Dr. Huang's presentation. So if you take an alpha ruthenium chloride, and it is actually not a quantum spin liquid because it orders around 7 Kelvin at zero magnetic field. But if you apply magnetic field, even with a fairly modest magnetic field of about 7 Tesla, you can suppress this magnetic order down to 0 temperature. So magnetic order has disappeared. And if you actually apply a larger field, you will actually basically realize something more a conventional or a trivial polarized state. But between them, there is actually sort of a sliver of phase, which seems to be something very unusual. And what they claim is that this is actually a Kitaev quantum spin liquid phase in this red area here. And how do they know this? And they actually show this by, if you do measure thermal transfers, then you can actually show this. And then I guess yesterday we heard that one of the things about these kind of quantum spin liquids is they are almost always insulator. So it is very difficult to study them using more conventional techniques like transport, electrical transport, and so on. But you can still do thermal transport studies. And it turns out that this is a very important tool for studying quantum spin liquids in these days. So most important thing here is that what they measured is a sort of a kappa xy, so this is a diagonal term or the off-diagonal term of the thermal transport. And if you measure the whole coefficient, then they actually have a plateau only in the region of this red region. So that's basically when they say that this so-called half quantized. This is annoying. So half quantized value here is a signature of Kitaev's quantum spin liquid. So this is a remarkable result, and this actually really kickstarted all the interest in this material, and then really gave life into this field. However, about 5 years into this sort of a first realization, there is a still controversy about what's really happening here, and the reason is because there has not been a sort of clear-cut follow-up study that confirms this work. And the situation is somewhat multiple, a little bit unclear. So there are actually two aspects of thermal transport that I want to mention. One is, so people have tried to replicate this thermal Hall quantization or quantum thermal Hall effect result of using Matsuda's, and then there is a sort of mixed result. So first, von Ong's group at Princeton reported that they couldn't reproduce that. And then the Hide Takagi group now and Max Planck in Germany actually say that no, actually they can replicate that. So this half quantized state and this temperature region and this magnetic field region. And then Louis Taliaferro group sort of said that no, I think they cannot even get to this point. So there is some mixed message, and then these are all respectable, very well-known group in the world. So I think that we should take all of them seriously. The second aspect, which is also interesting, is so von Ong's group, when they actually published this result, although they could not see half quantized sort of a thermal Hall effect that they were trying to find out, but they found something different, which is also interesting. And they said that if you measure just a regular thermal conductivity, kappa XX, and in this region or sort of a high field or sort of, I guess, moderate field region, what they found was actually oscillatory behavior of thermal conductivity. And then the interpretation of that was that this is actually coming from the quantum oscillation of thermal conductivity due to fermionic spin, so spin on Fermi surface, basically. So then that is actually naturally what you expect in some other types of quantum spin liquid, because you actually what's important about quantum spin liquid is sort of some kind of anionic or fermionic degrees of freedom, and one example is a spinons. So that actually is interesting discovery. So it is basically the story there is that it is maybe not the chiral Kitaev quantum spin liquid, but maybe another type of quantum spin liquid. But follow-up studies actually kind of put cold water onto that story, because again, the Takagi group and the Taliaferro group said that no, actually they are probably not really quantum oscillations, but they are just some kind of signature of some type of phase transitions. Okay, so that what kind of phase transition we don't know, but so that's what basically these guys are claiming, and so I'm actually kind of provide samples for these studies. So that's actually unclear. So the situation here at the moment is unclear. So nothing's clear about this material. Why is that? And I think currently I think everybody is resorting to the sort of a kind of idea that it is sample dependent. So that's a very easy way out. So what we are trying to get at is so what kind of sample dependence can explain this? What are they talking about? What are these people talking about when they say sample dependence? And these are like not the first material that they studied in the first couple of years. So for 10 years, people have developed a lot of very high quality way to make high quality samples. So these are actually not bad samples. They are all very good samples. So why actually are we still talking about sample dependence? So that's the main part of this talk. Okay, so let's start with that sort of a baseline. So if we actually grow ruthenium chloride crystals, you get something like these many different types of crystals. So you can sort of kind of easily see that these look pretty bad and these look good. But what I'm basically trying to say here is that it turns out that, long story short, only when you get sort of really like nice thick chunk of crystal, they have a good quality. And if you have this kind of a shape like this, a plate-like, and this is actually a fairly large sort of flat plate, and then they actually are not that great in terms of crystal quality. And the reason or the way actually we can tell that is there are two ways, right? So if you measure the phase transition, magnetic phase transition of these materials, and these kind of bad-looking crystals will show these multiple transitions, and the good crystal that looks like this will have a single, very sharp, specific heat peak, and that signifies this is a high-quality crystals. And if you look at the X-ray diffraction pattern, then the good crystal, or we call this thick crystal, have a very nice diffraction peaks, as opposed to these diffuse streaks that is found in sort of crystals that looks like this. So that actually is kind of the hallmark of crystal quality that everybody now uses, and then we sort of understand that that's basically the main thing. And that means that pretty much all the samples that we are talking about in these different studies are good quality, high quality crystals with a single, very sharp, specific heat transitions. But even in those crystals, there is actually huge variety of sort of a sample dependence. So here are sort of some studies illustrating the difference, especially in the thermal conductivity or thermal transport properties. So here there are like 4 different so-called high quality crystals. They show very different levels of thermal conductivity when you measure these things. This was done by Kitaev group. And this is, again, from the Matsuda group, sort of similar works. There is a difference in the sample dependence in the thermal conductivity and sample dependence in the oscillatory behavior and so on. Okay. And what we found also was that even though, so for example, here, you seem like good crystals should have a single transition around 7 Kelvin, but some crystals have a 7 Kelvin, and some other crystals show sort of a slightly different crystal temperature. So there is actually sort of this type of difference in sort of kind of a sort of narrow region of the transition temperature also shows some sample dependence. So all these things points to for us to actually look at the crystal structure a little bit more carefully. So that's basically what we are going to talk about. The first thing that we want to talk about is structure and magnetic anisotropy. So to basically answer the question about what are they different, what's the difference? The main basically story is this. So here's a honeycomb lattice, a single layer, and you have to stack them. And unfortunately, actually, it doesn't stack AA type of a stacking in real materials. So there's some other way of stacking these things are found in the real materials. So so now everybody sort of understands and agrees that the good quality crystal structure of alpha ruthenium chloride at room temperature is sort of obtained by doing this kind of stacking. So you take the honeycomb layer and then so define the axis of A and B in this way. And then if you actually stack the upper layer by 1/3 of the direction along the minus A direction, and so on in this direction, that is so-called the C2M structure. And we all know that this actually is the direction. So, so this is basically understood as crystal structure at room temperature. But at around 150 K, all the alpha ruthenium chloride structure goes through structural phase transition. And it was actually kind of uncertain what kind of structural transition is occurring. But now I think because we actually have some good data, we understand that what's happening here is that at low temperature, stacking pattern is changing from this to this type of thing. So instead of actually stacking along the A direction, now if you take this same layer and then stack along the B direction, then you get something like this. So clearly there is a different symmetry, because here it is twofold symmetric, but this one actually you recover like the rotational or C3 symmetry. One additional thing that you have to consider is that now imagine going from here to there around 150 K. There is actually no reason for this to go into that direction versus this direction. So there is a very natural twinning happening around 150 K. So even if you start with a perfect crystal at room temperature, when you want to do the measurements, so you cool down, then you basically a flipping coin and then you can get this or that. And most likely you'll get both. So you're almost always you will get a twinning of your crystal, perfect crystal, by the time you reach this, whatever, 7 Kelvin, 5 Kelvin, where you want to do your measurements. And these things will definitely depend on the sample. So that's basically the origin of the sample dependence, even if you start with a very, very good quality crystals. However, you can get lucky, and you might actually get just one type versus this type. And it turns out that we actually have such a sort of a lucky situation here, because we in this particular sample that we studied, we have found something very interesting, because this is high temperature, very, very well-defined sort of a super sort of a Bragg peaks. But when you go to low temperature, then you can sort of see that there's a sort of Bragg peaks sort of occurring, this is going from this way to tilted this way. And that is actually significant, because that signifies that it is actually now stacked along the B direction. And you can ignore actually these streaks, because these are, this is a logarithmic scale, so it is actually quite small. And if you actually look at these, comparing these two things, then you can easily see that there's a shift of the Bragg peaks from this integer positions to 1/3 positions. And that is basically signifies this one. So that's basically what we see as a structural transition going from here to there. And what's significant here is that we don't see much of the other twinning. So if you actually have a twinning happening in both directions, then the Bragg peak will go into this way or that way. So that basically means that you will actually see these two peaks. So there are 1/3 as well as 2/3 peaks. And that is basically the signature of a twinning. And many cases, in almost all the experiments that we did, we have actually, the unfortunate thing is that you actually have to look at sample by sample. And sometimes you get actually lucky, and then you have almost twin-free samples. And in that case, you can sort of study the crystal structure and magnetic structure very, very carefully. And in other cases, you actually have mostly twinned crystals. And it's interesting that we only see twin-free samples when the Tn is about 7.2 Kelvin versus Tn is 6.5 Kelvin in some other twin samples. Okay, so that's the stacking. You might actually, at this point, if you're, so a lot of your theorists, so you're thinking, why do we care, right? So it is Kitaev model. It's a two-dimensional model. Why should we care about the third dimension unless we want to make actually bilayer systems? But so in that sense, actually, does the stacking matter? And it turns out that it may. So what we have done here is actually to confirm whether or not Kitaev layer itself. So, right, so there are two things, right? So the crystal structure can be determined. The global symmetry is determined by the stacking. But if you just look at the single layer might be still completely C3 symmetric honeycomb layer. And actually, is that true? So that's the hypothesis we wanted to check by measuring the Bragg peaks along this direction, and then rotate physically sample by 60 degrees and measure this direction, and then measure this direction. And then clearly, at low temperature, you have all equivalent positions. So this is great, because that means not only is this symmetric in the C3 symmetric globally, but locally it's also symmetric. But at high temperature, then that's not the case. So it means that somehow, when you actually stack along certain ways, the stacking determines local symmetry. So that is actually what we have found. So honeycomb layers is distorted at high temperature, meaning if you stack in certain way, somehow the layers know that it is stacked along that way. And this also means that stacking disorder implies disorder in exchange interaction. So then actually, I guess you have to sort of think about that. If you have a lot of this sort of mixture of this and that, for example, then at you can no longer think of this as a sort of purely isotropic Kitaev model. And we have a proof of that, sort of going beyond that, because this is a structure. But if you look at the magnetism, the magnetic susceptibility as a function of temperature for this very high, the single twin free sample, below the transition, it doesn't matter which direction you apply magnetic field, susceptibility remains the same. However, if you actually go beyond at higher temperature, depending on which direction you apply field, the magnetic susceptibility changes. So that again suggests that there is a difference between magnetic Hamiltonian or magnetic interactions below and above this structural phase transition. And that's, you can actually quantitatively describe these changes using a so-called anisotropic JK gamma model. And this was actually, this is just using high temperature series expansion. And I'll come back to this model, which is actually kind of the main and interesting model that a lot of people are using. Okay, so that's basically a story about the structure. So we think the main take-home message is that there is a structural phase transition that screws things up. But basically, you have to be lucky to find a twin-free sample, and using that sample, you can actually find what's really happening in this material. Otherwise, it'll be very difficult to actually find that out. So now that we have this very nice crystal, we can actually look at the magnetic structure in detail. So let's look at the magnetic Bragg peaks. And by the way, we have done this all using X-ray or so-called resonant X-ray scattering. And then the reason why we do that is actually going to be clear in a moment. So here, what we are plotting here is that this is structural Bragg peak, and this is magnetic Bragg peak. And magnetic Bragg peak occurs in the 2D brilliant zone around this point, and that point, so-called endpoint, is consistent with the so-called the zigzag magnetic order that is shown here. So now that we have a single or one type of stacking, we can actually figure out how is the three-dimensional magnetic structure look like, as opposed to the zigzag magnetic order, which is just a two-dimensional order, but we do have actually three-dimensional order. And here's actually kind of the two options, right? So we only have this type of crystal structure stacking. And what we are seeing here is that the plot of this one is you take this and you look from this side. Okay, so you are looking down on the A-axis and this thing. So we have this zigzag, and these are basically zigzag chain running outside of this lay plane, and this is another zigzag, and this is another zigzag. So you can have zigzag stacked in this way, or zigzag stacked along that way. So there are two options, and we can actually tell which one is right because you can easily see that this has a 6 unit periodicity. This one has 3 periodicity, and our Bragg peak actually occurs at 1/3 periodicity. So that means that this is this type. So now we have completely identified the three-dimensional magnetic structure of this thing because we actually have a twin-free sample. But if we were to have actually other type of stacking twin, then you will actually have this type of things. The reason why this is important is basically this actually determines what kind of interlayer coupling you can get, right? So the difference between this and this is that going from go directly from this spin to this spin, this has a ferromagnetic interaction, but this one has antiferromagnetic interaction. So this basically distinguishing between this tells us that the interlayer coupling should be antiferromagnetic rather than ferromagnetic. And that is what we have found here. And so the sample dependence, we could see, as I told you, that there's a small difference between these two samples. So one is 7.2 and the other one is 6.5. And the difference is very clear in this order parameter measurement because it is not just thermometry or anything weird. So one sample clearly shows a magnetic order parameter going down at 6.5, another sample showing 7.2 transition. So the last thing that it's probably the most important thing about that the way we have done in this X-ray study is that we can actually study magnetic moment direction very, very carefully using resonant X-ray scattering. And you might think that why is it important? And it turns out that it is one of the quantities that really tells a lot about the magnetic Hamiltonian. And so So take this, the octahedra, and the spin can point to either that way or that way. And so this was worked out by Shalupka and then Kulin. So if you take this, and if you take so-called JK gamma model, so K is the Kitaev interaction, and gamma is sort of a symmetric off-diagonal interaction. So it's basically coming from the spin-orbit coupling in your exchange Hamiltonian. And depending on the sign of Kitaev interaction, antiferromagnetic versus ferromagnetic, you can basically point the spins along the oxygen direction or the plane of this octahedra. And also by turning on the gamma, so gamma sort of term is sort of effectively acting as an anisotropic interaction. So if you turn on the gamma, so for example, take a ferromagnetic Kitaev interaction, then with the zero gamma, you will actually have something like this. But as soon as you turn on the gamma interaction, it will sort of quickly switch to this so-called AC plane. And then as you increase gamma interaction, you are gradually rotating this spins away from this plane towards the equatorial plane of the honeycomb plane. So this measurement alpha is actually very important in determining the size of gamma interaction versus size of Kitaev interaction. And this is a sort of a calculation in that paper showing that if you increase the gamma, then you will reach sort of a plateau around the 30 or 35 degrees. So with that, about 3 years ago, we have published this paper showing that we can actually determine this angle alpha very accurately. And this was work done by my former student, Jennifer Sears. So here, what we are using is so-called resonant X-ray scattering, resonant elastic X-ray scattering. So this is magnetic Bragg peak position. And then it turns out the intensity of magnetic Bragg peak, I, is proportional to Kf dot S squared. Here, S is the moment direction, and Kf is the photon momentum direction. So Ki is the incoming photon. It scatters from the sample and goes out. So if Kf and then moment direction matches, then you will have large intensity. And if they are perpendicular, then they will have small intensity. So by rotating your sample, then you are basically rotating your spins. So right, precessing your spin direction or the moment direction, then you can basically see what which direction these moments are pointing at. And we have done that measurements, and then you can fit this into sort of these different types of models. And this is a completely geometry. So this is not a complicated fitting. So based on this, you can easily figure out the angle between the spins and the honeycomb plane matches really well with about 35 degrees in this geometry instead of that geometry. So that means it is, the conclusion here is that it's a ferromagnetic Kitaev interaction, and then antiferromagnetic gamma interaction is required, which is relatively large. So what we have done is we revisited this measurement, and the reason for that is actually going to be clear in a few moments. So for our really nice sample, we got this one. So this is a measurement, and you can fit this with all these different angles, and so around 31 degrees it looks about right. And then we actually looked at this another sample which has a heavy twinning, pretty much looks the same. And you can actually look at this a little bit more carefully by where this goes to zero. So this is actually even better measurement. And you can sort of see that this goes to zero here and this goes to zero here. And there's a slight difference because the peak position and then all the exponential geometry is different. But overall, I think there is agreement that this is about 31 degrees plus minus 2. And this is our previous result, which actually we got sort of 32 plus minus 3 or 35 in this case. The reason is it doesn't really matter, right? So this sample has 6.5, this sample has 7.2 Kelvin, this sample has 12 Kelvin. So they are actually different quality of samples, but it turns out that their moment direction all in the same direction. What does it mean? It means that, at least according to this measurement, the in-plane Hamiltonian is it doesn't really depend on the sample. So which is good news, right? So because then we don't actually have to worry too much about this. So then where does the interlayer coupling come into play? And that probably comes into play to determine the transition temperature. So in some sense, interlayer coupling is important for determining the transition temperature, but it is not big enough that it changed the magnetic structure. So that's basically the main conclusion here. And this is a kind of like my sort of attempt at sort of a domain one. I mean, this is a one part that I sort of said the domain one here. So why are they different, right? So then one sample is completely clean and you have 7.2 Kelvin transition, and another sample with a lot of twin domains, then you have a suppressed Tn. So I think that is actually kind of the conclusion that we get. And so that implies the interlayer interaction is important for magnetic order. In some sense, that's maybe not surprising, but still, I think it is something that's that people haven't really thought too much about it. And obviously, interlayer interaction will be important for realizing something like the bilayer, the model that we just heard about. And sort of interlayer coupling is important. Then the question is the interlayer magnon important? Because the recent study actually suggested this interesting half quantized thermal Hall effect may be due to topological magnons instead of actually Majorana fermions. So clearly the magnetic structure and the magnetic interaction between interlayers will be important for these kind of things. So I'll stop here. So this is a basic summary of what I have talked about. So I'll sort of, I guess, time is up. So I'll stop here, and I just want to point out there are two things that we studied. One is the structure. So we actually do understand now that why actually there is such a big sample dependence among samples because of the structural transition and twinning. And for good sort of a twin-free sample, we can actually do a very careful, very sort of measurement of magnetic structure and magnetic anisotropy and so on. And then the end result or the conclusion is that the interlayer coupling cannot be ignored. So I think that's basically the main message. Right. Thank you.
Yes.
Yeah.
Usually, the magnetic structure over many layers.
Yeah.
So you should many possibilities.
Yeah.
Can you go back to? Oh yes, this one. Yeah. So I couldn't understand clearly.
Yeah.
So in the first case, so that case we have a 3-layer unicell.
Right. Yeah.
If we have that magnetic ordering. But if we consider the other one, the second one, then you mentioned that the magnetic unicell should be a 6-layer.
Yeah.
Why that happens here? Is it related with the crystal structure?
No, so they have the same crystal structure.
Yeah, same crystal.
So it is basically how you stack so this is a honeycomb layer with a zigzag order. And going back, so this is zigzag order. So you can basically put zigzag order here over here and then do that way, or you can go the other way. So they are different. So looking down, so we are basically looking at the zigzag. So you're looking at the zigzag direction here.
Yes.
So you're basically putting the next layer onto this way, so going up in this direction. But here, you're putting this in the sort of kind of reverse direction.
Oh, is that because the layers are shifted by 1/3?
Yeah. So this is yeah.
Okay.
So this would be 1/3 kind of minus 1/3, and this would be 2/3.
I see.
Yeah.
Thank you.
Yeah. So they are different.
Is there any change of structure and magnetic structure in the presence of external magnetic field around the 7 Tesla or 10 Tesla? There are no changes.
The answer is we don't know, because so if we didn't actually study in under magnetic field. Is there? Yeah, so I think there is no reasonable way to answer the question, even from yeah, I don't think people, I mean, even the neutron scattering, right? So in neutron scattering, yes, actually, neutron scattering found that actually magnetic structure changes at high field. So first thing, actually, so okay, magnetic field does affect magnetic structure. So that is actually, I was thinking about the crystal structure. Crystal structure, I don't think there's information, but magnetic structure is changing. First of all, I think as you apply fields, there's a domain basically, so your magnetic domains are killed, and then you basically gain single magnetic domain structure or spin flux transition happening at around 1 or 2 Tesla. And beyond that, about 6 Tesla, I think there's a neutron scattering result from Oak Ridge that says that magnetic structure changes. Yeah. So there's one study claiming that this happens at high field. So this is the zero field structure that we have confirmed. So what they say is that actually this might happen at high field, yeah, before it is killed by the magnetic. So yes, I don't think there is a clear understanding why that is the case, but it was just observation from neutron scattering.
I have a simple question. So the twinning only happened at the low temperature.
Right.
So is it any way when you thermal cycle they will stay exactly the same when you warm up it?
That's a good question. I think there is a study of repeat of this thing. So what we don't know is that if you actually start with a sort of a like single twin sample like this, and as you cycle through many times, will it actually become more like disorder like this? That we don't know. We haven't done that. But there are actually people have done sort of a decycling experiment, and then what they found was that sort of ratio between these twin domains seems to be more or less the same even after many cycles. So these twin, I mean, it's twinings do not happen completely random, right? So it is so I think there is some kind of defect that is actually responsible for something like this. What we don't really know, so all these things we assume that it is completely the stacking defect, but nobody really knows whether or not there's an in-plane defect. So this, we just don't want to accept that, and I think we don't want to actually know what happens there. But I think that's something that we don't really know. I mean, you cannot have a perfect crystal, so I think it's a possibility. But I think mostly, I think we're trying to sort of think of this as a more stacking related defect and stacking related disorder rather than what might be happening in the in-plane. But it's clear. So if there's an in-plane defect, that might be kind of responsible for nucleating is twinning kind of thing. So then it'll be reproducible, even though you actually heating and cooling cycle is repeated. Yeah.
So did you grow your samples in your lab?
My student.
Your student. I wish I had the same problem. So I wish also has a lot of twins, but people had a lesser fit to the twinning, something like a special treatment.
Yeah.
So you don't have a twin effect. So did you try something like both kinds?
So the problem here is that the YBCO is auction sort of controlling all these things can happen at high temperature. So, but this one happens at 150 Kelvin. So I guess to do that, you basically have to find a recipe to how to cool, right? Like doing some kind. So I mean, you can think of a lot of different things, right? So apply some kind of strain and then cooling. Apply magnetic field and cooling. Apply, I don't know, like sort of. I mean, you cannot apply electric field because it's. I guess you can apply electric field. I guess then try to cool. So these things have not been tested. So you can sort of, but it will be a lot of work. You can sort of imagine that, because it is not one sort of YBSL sample. Once you actually make the sample, that's good. But finding the recipes every single time when you do the experiment, you have to basically follow this recipe to cool down.
Sure.
This is difficult. So, yeah. I guess these are things that if it's important enough, then people will do it.
Seems like this is important.
Yeah,
Really
yeah,
important here.
I think so, but yeah. Okay.
Any other question?
So based on your talk, so interlayer coupling might be important, right?
Yeah.
To understand this material.
Yeah.
Do you have any idea about the size of the interlayer coupling?
I don't. It's small, but that's all I know. You can guess, right? So if the difference between, so I don't know. So like there's a transition temperature Tn difference between 6.5 and 7.2. If it is coming from layer coupling, that's probably, it's not directly that. Probably it is sort of that with some kind of sort of a multiplication of the main coupling and that kind of stuff. So because so that's another thing, right? So far people have been thinking about magnetic order as purely in plane physics. But if interlayer coupling is important, you can actually have no order in the two-dimensional system, but actually you can make order because of the interlayer coupling, which is the case in the cuprates. So for example, right? So then, so when you actually put in interlayer coupling, the sort of understanding the magnetic order becomes a slightly different, and then, but estimation of the energy scale, I would go with this difference in the T. Yeah. I think there was a, yeah.
So the question is related to the experimental measurements of the thermal conductivity. So does it make sense to talk about the thermal Hall conductivity without in terms of magnetic field in this system?
Okay, I'm not an expert, right? So I'm not the thermal transport person, but to me, it seems like it has to be a magnetic field. Hall effect sort of kind of almost by definition requires magnetic field.
Yeah, because there are very like in this, if you think in terms of magnon, there are very curvature. There may be higher order contributions, anomalous.
I don't know. I haven't answered to that.
Yes. Can you conceive any local measurement to determine interlayer coupling? Is that something that's possible within present experimental technique?
Actually, what do you mean? So is there any other example that you
Any
so
local-
I'm a scalar person. So when I measure interaction, I measure dispersion relation. Right. So to measure the so if you have a perfect crystal, you measure the dispersion relation along the Z direction, that the bandwidth tells you the coupling, interlayer coupling. But my guess is it's too small to measure with the resolution of these things.
Something like Raman scattering, that have resolution good enough to really look at the
No.
interlayer.
So right, so it's thinking about the interlayer coupling as a magnon dispersion, right? So that's the sort of really the most direct way of measuring the coupling strength is measuring magnon dispersion relation along all directions, and then along the Z direction you have to measure the magnon dispersion, and to measure dispersion you have to measure more than one Q points, right? So Raman will be just a Q equals 0 point, so that will be difficult to determine. Having said that, it's not the only way actually that you determine the dispersion relation, but coming from neutron scaling background, that's how I would determine. So I don't know if maybe there are other methods. You cannot do STM. I don't know if you do that, so. So there are many limitations, yeah. But I guess another way is actually fitting some susceptibility and that kind of stuff, and then trying to see actually if you can determine from it. If you can actually come up with a model to determine the TN, we're using based on the interlayer coupling, that is one way to determine this. If you know, assuming that you know the intra-layer couplings, then interlayer coupling really determines the TN according to a certain model. Yeah.
Any other questions? If not, then we thank the speaker again for